subtraction, just as we did with the decimal numbers, you form the ones complement of the subtrahend. Once you have formed the complement, it's just addition. You add to the minuend. After addition, check the carry bit. If the carry bit is 1, you know the result is positive. Then knock off the carry bit, do the end around carry. If the carry bit is absent, the result is already available in the complement form. So that is a procedure is just identical to what we put with decimal numbers. As shown examples here. See here, first case. 0, 1, 0 minus 1, 1, 0. 1, 1, 0 is represented as its 9's complement. I'm sorry, 1's complement here. 1, 1, 0 is represented as a 1's complement. I'm adding the 2. I get this as the result. There's no carry here. The carry is absent. It implies that the result is negative. And 0, 1, 0 is the complement. You can check up whether that is okay. This number is actually, this is 2, this is 6. Okay, 2 minus 6 is minus 4. Huh? Hmm? Sukumar has done it intentionally. I put please do the correction. Okay, next one is 1101.11 minus this number. It is here only, the binary point is only for alignment. So this is okay, no? 0, 1, 0. It's okay, no? It's okay. Oh, I don't believe him. It's okay. This is okay. You get a carry here. You get a carry here. This is actually a carry. Okay, it's a slight misalignment. It's a carry here. So do the end around. The result is positive. The carry bit shows that the result is positive. You do an end around carry. Add, take that 1 out here and add it here. You get this as the result. Unlike the decimal case, with binary numbers, working with complements is easy. You have to take every, therefore you have to only complement, nothing else. Every bit you complement, you do addition and do an end around carry. That way it is very easy. There is no need for any prior comparison of numbers. There is no swapping of this and that as you do with regular conventional subtraction. 2's complement is just similar to 10's complement. You form 1's complement, add a 1 at the right end, do 1 from, get 1's complement, add a 1 at the right end, then you get 2's complement. I'll take an example here. You have set up binary numbers. For a change, they are aligned here. They are 1's complement, they are 2's complement. You can check out that that is okay. Here it is 1, 1, 1, no more. So here, see, this one is 1, 1, 1. It's 2's complement, every bit are complemented. To that I added 1, I'm sorry, 1's complement, every bit are complemented. To that I added 1, I got 2's complement. Same way with other numbers. Is okay? Subtraction, you form 2's complement, you add to the minuend, you check up the carry. If the carry is present, the result is positive. Ignore the carry. If the carry is absent, the result is negative and it is available in 2's complement form. And it's okay. Base is okay. As one same examples I have taken here. complement is this? We have taken complement. I can proceed. Now coming to multiplication. When you come to binary multiplication, things are in a way they are simpler. Just to see here, individual digit multiplication is very easy. 0 into 0 is 0, 0 into 1, all these are 0, 0. Only 1 into 1 is 1. In all other cases it is 0. As single digit multiplication chapter is over. Multi-bit multiplication, we do as we do with decimal case. See, multiplicand is a multiplier. I want to multiply 1011 by 1101. So I take the partial product, add them, just as we do with decimal numbers. See, I taken this 1, put it here. When I multiply, see that. I want to multiply the 2. This bit I take is a 1. This 1 I multiply by this. When I say multiply, you have to do nothing, you have to reproduce. Because only 0 and 1 are there, you just simply reproduce. When I reproduce, I get a 1, 0, 1, 1. Next bit is 0. So the partial product with this number will be 0. So I go shift by 1 position, 0, 0, 0, 0. Next bit is a 1. Same partial product I take, shift by 1 position, 1, 1, 0, 1. This bit is a 1 here. The partial product will be again shifted by 1 position, 1, 1, 0, 1. This is a partial product of this fellow. For this fellow, I get the partial products. Then I just add. Not add this one. This one will give me a 1 here. 1 plus 0 will give me a 1 here. No carry. 0, 0, 1 will give me a 1 here. No carry. 1 plus 1, it will give me 1, 0 plus 1, 1, 1. Is all right? 1 plus 1. 1 plus 1, it gives me a 0 and a carry. So that when I add this, I get a 1, 1. That 1, 1 I put here. This one is a carry for me. I take that carry, add to this. 1 plus 1 is a 0 and a carry. That carry I add here. I get 0, again a carry, I add here, the 0 is 1. I hope I have done it properly. Procedure is clear? It is much simpler than what we do with binary numbers in one sense. You have no multiplication involved, only you have to reproduce or put a 0. But the point is, if you take a number, it involves very large number of bits. If you are prepared to put up with that, it is very easy. Okay? You have to do some practice, then it's very easy. You can just check up this. This number is actually, this is what, 1 plus 4, you can just take it up. That's as far as the multiplication is concerned. So the multiplier bits are essentially used as indices to shifted position to form partial products. Get the partial products, add them. I'm not telling anything big, we already do, but I'm just repeating with binary numbers. Division. I just done a division here. Dividend, division, whatever we do conventionally I have done here. See here 1011 divided by 11. I put 1, 1, align here. When I align, I find that this 1, 0 is less than this 1, 1. So I put a 0 here. Alright? And then I shift 1, 1 to the next position. 1, 0, 1, 1, 1, 1. Can I write that? No. Who says no? This one, that's it. Oh, there's a Bangalore and Amritsar. I got a number 1, 0, 1, 1. I have to divide this by 1, 1. I put here 1, 1. I simply write here 1, 1. I try. This number is larger than this. So I have to shift it and then proceed with, since it is larger, I put a 0 here. I put a 0. Then I put that number here 1, 0, 1, 1. I repeat with 1, 1 shifted like this. It's alright? No, I messed up. No, I got here 348, okay, 3485. I have to divide this by 43. First I put a 43 here. I try to subtract. This 43 is larger than this. I put a 0 here. 3485. I put here 43 or multiple. It's okay? Okay, not 43 into something I have to put, no. I think 8. I might have to put here 8 into 43. 8 into 43 will give me I put an 8. I subtract. I get a 4. Then I take this 5 here. Then I put 4, 3. I get a 2. I get a 1. Okay. Two things. One is the procedure. Second is my algebra. Algebra is okay. Same thing I do here. I take this 11. See, when you do subdivision, you will not put like this because you know what you are doing. You know what you are doing, so you won't do, directly put it here. I'll just put, just to get a feel of the procedure. I put 1, 1. I know this number is larger than this. I cannot do the subtraction. I put a 0 here. I bring it here. So the same number I reproduced, I brought it here. Now this number, this 1, 1, I am comparing to 101. This is smaller than that. Okay. Now actually we have to put only a 1 or a 0. To that extent is simpler than decimal number. I have to put a 1 or a 0, so I put a 1 here. I put a 1 here. I will simply subtract from this number this. I will get here 0. This is less than this. I borrow 1, 0 minus 1 is a 1, 0. I bring this 1 here. Now what I am saying is, I do a blind procedure. What you are saying is right. I just blindly, I took this number, I am putting like algorithm, took this number, put it here. I compare. This is less, actually as good as, I reproduce this number, I shifted this. Okay, I could have done what you are saying. Yeah, okay, correct. Again, I put 1, 1, 0, 1, 0 minus 1 is 1, 1. This is less than this. So this is a reminder. That's the quotient. Thank God you have got same answer. But I could have messed it up here. The procedure is just similar to what we do with decimal system. There's no change. Okay? Just there's no change. Quotient is 0, 1, 1. That's a binary number. Now, to know whether that is written or you have to convert to decimal number and just to see. This 1011, decimal number 1011 is what? 1, 2, 3 plus 8, 11. 11 divided by 3. 8. 3. I know decimal to binary to decimal conversion. I know binary division. I even know decimal division. Huh? No, I did the conversion here. I checked up. This I have done for checking. So, and see, please understand. Earlier we did decimal system to get a feel of what it is. Now I am doing binary number system. Binary number system, there is no decimal system. You understand, all numbers are binary. There is no 1, 9, 8, nothing like that. The whole world is only zeros and ones. You understand? So you cannot ask me, why can't you put it in as a decimal number? You understand? Only binary number exists here. Answer in binary number. Anything you ask, I give only binary reply. Yes or no type of reply. Nothing else. It's okay? Binary number. This is what I have done here. This is a quotient. 0, 1, 1 is a quotient. This is a reminder. You understand? What you have to understand is nothing else exists here. Only in 0, 1. There's no 2, no 3 business. None of them are there. It's alright. It's okay. Now maybe in the afternoon we'll do something else. We'll go to hexadecimal where we say that beyond 9 there is something more. You have just to extend the concept. You have to tell yourself, okay, you have to tell yourself the system is different. The whole system is different. You have to understand the system is different, but where they match, in what respects they are identical or similar, and where you can just check up one with the other. Say for example, what result I got here. If I know only binary system, I will do only with this. If I know only decimal system, I will do with this. Now I know decimal system very well. You have given me this binary result. I don't know whether what you are doing is right. Just I want to check up, so I convert it and did this. Okay, is all right? Why you are doing all this is in digital system, you work with only binary numbers. You work only with binary numbers. But in our day-to-day affairs, we are familiar only with decimal numbers. So we should know binary numbers, we should know decimal numbers, and we should be able to convert from one to the other. So we will go through this and go through conversion also. It's alright? So much about the binary system. We can continue for some more time. We can continue up to 12:30. It's alright? We'll continue to 12:30, break, and then 2 o'clock. We'll meet at 2 o'clock. I have prepared, like, what we give to children. I have prepared a table here. This is a table of numbers in the octal system. In the octal number system, there is room for only 8 digits. The digits are 0 up to 7. 0, 1, 2, 3, 4, 5, 6, 7. There is no 8 and 9. Then I go for 2-digit number. 1, 0, 1, 1, 1, 2, 1, 3, up to 1, 7. Then 2, 0, 2, 7, 3, 0, 3, 7, 4, 0, 4, 7. I go up to 7, 0, 7, 7. I don't know how I wrote down this. This is a new system. Not 100, 100. So this 7 will be what? 7 will be actually 49 plus 7, 56. This actually is 57 in decimal system. No, this one. This will be. Just to see here, this I put a number, octal number 1, 2, 3. This 8 signifies the radix. That means that number is a number in the octal system. Okay, 1, 2, 3, 8. Actually, its value is, in decimal number, its value is 1 into 8 raised to 2 plus 2 into 8 raised to 1 plus this 3 into 8 raised to, actually it is 8 raised to 0. Okay, it is 8 raised to 0. That gives me 83 as a decimal number. Is it alright? So, okay. Now, same thing I proceeded further here. 1.23 radix 8. It is 1 into 8 raised to 0 plus 2 into 8 raised to minus 1 plus 3 into 8 raised to minus 2. Just this decimal number is entirely different. You please understand the difference. The decimal number, if we just to take here, 1 into 8 raised to 0, 1 multiplied by 8 raised to 0 is 1, then 2 into 8 raised to minus 1 equal to 2 multiplied by 0.125, that will give you 0.250, then 3 into 8 raised to minus 2, that will take more time for me. 8 raised to minus 2 will be actually equal to 3 multiplied by 0.01565. That will give 0. Okay. Thank God it's okay. Yeah. 1, 2, 3 is 83. Oh, you are talking number theory. What is more you are saying? Oh, what you are saying is if you shift it by 2 positions, it becomes more. You are talking of a theorem in number theory which I am not sure of. Since I don't know, I think I'll go to the next one. Just like octal system, you have got a hexadecimal number system. In the hexadecimal number system, you use 16 individual digits. You see here, I can have binary system, ternary system, etc., etc. But we talk of binary system. Anything? Okay. We talk of binary system, octal system, hexadecimal system. It is because the octal system, see, just as we are having in binary system, we are having 2 as the base of the radix. In octal system, we have 8 as the radix. In hexadecimal system, we have 16 as the radix. This 8 is 2 raised to 3. 16 is 2 raised to 4. Since this is a power of 2, it is easy to work with that. With a binary number and octal number, it is easy to convert up and down. Same way with a hexadecimal number. Just as if I am having a number to the base 10 or a number to the base 100, they are very closely related. So it is easy to convert one to the other. So wherever you work with a binary system, if you want some change, you go for an octal system or a hexadecimal system. It is easy to change from one to the other compared to working with a decimal system because there are powers of 2. Coming back here, with a hexadecimal system, it has a radix of 16. There are 16 individual characters which use as digits. Radix of 16. The convention is use all the characters that use in decimal system. 0, 1, 2, up to 9 you use. After that, you require 6 more characters. There are 16 required. You require 6 more characters. The convention is use A for the next one, B, C, D, E, F. A has a weightage of 10. B has a weightage of 11. C has a weightage of 12. D has a weightage of 13. E has a weightage of 14. F has a weightage of 15. So in hexadecimal system, the way we conventionally represent, we use these as the individual digits. 0 up to 9 as we use in decimal system, then A, B, C, D, E, F as we as the other additional characters. With this representation, we can represent any number in hexadecimal form. I have taken here 1, 2, 3 to the base 16. Just as the same number we took earlier, what we took as 1, 2, 3 to the base 8, I have taken the same 1, 2, 3 to the base 16. If I convert that into decimal form, I get, I put it somewhere, no? Oh, I think this is radix 10, right? That was it. Actually, Kushuman said he'll put all this in the Vidya. I think before that we'll change all this. So, it has a value 291, whereas if I represent it to the base 8, it had a value only 83. Here it is 291. Same way, if I take hex number FE, it is 15 multiplied by 16 raised to 1. So that as weightage is position 1. Then E with weightage 0. So 14 into 16 raised to 0. 14 into 16 raised to 0. That gives me 254. Is it alright? 240 plus 15. 254. Is it okay? I taken the same hex digits. I put a radix point here. Hex point. I put it here. It is F point E. The magnitude is 15 multiplied by 16 raised to 1. Plus 14 multiplied by 16 raised to minus 1. Please correct me out. Actually, as we come closer to 12:30, we can afford to make more mistakes. I got a lot of ground to cover. Please don't ask questions and divert me, sort of thing. Algebra is similar, but I think I am not going into details here. The advantage is 8 is 2 raised to 3, 16 is 2 raised to 4, so they are very closely linked. In computer systems, you work with all the binary system, hex system, octal system. Anyway, you have to work with decimal system. I think we'll stop here. At 2 o'clock, we'll just go through the conversion. That is, Now, you have gone through the number systems. You should have mechanisms to convert from one system to another number. Binary number, I should be able to convert octal number or vice versa. Partly we went through. Binary number to hex, octal to hex, etc., etc. Now, binary to octal, it is easy. Binary to hex, it is easy. This is easy. But decimal is a bit more involved. Other number systems, it is more involved, so we use decimal as an intermediate. I'll stop here or will continue for some more time. You can stop, I think, no? You can stop and spend some time with conversion the output, then proceed with logic, binary logic.